Hey guys, so for the first assignment for the week, we're going to be learning about Le Chatelier's principle. Okay, so for that assignment, there's a few things to do. Okay, there's this note sheet, typed up notes for you that I want you all to read, and I want you to take notes on it yourself. So I think that will be helpful if you just on a piece of paper, just kind of as you're reading through these notes take notes on them. Okay. I am also going to take you through some examples so that you get some direct instruction on it, and that will be helpful, hopefully. In addition to that, there's homework problems you're going to be working through and submitting your answers. Before doing those homework problems, I would watch this video. Okay. So, this video, really helpful. I want you to watch it, take notes on it. There's a part in the video where at the end, he'll give you some kind of checkpoint questions. Pause the video and try and answer the questions, then hit play and it'll give you the answers. Okay, so what is Le Chatelier's principle? Okay, so Le Chatelier's principle basically says that if you have dynamic equilibrium, right, in an equation, you've got equilibrium. But if it's disturbed by changing the conditions, the position of equilibrium moves to counteract the change. What does that mean? Think about like a seesaw, right? If one person goes down, then the other one goes up, right? And vice versa. Or in the notes, let's look at the notes. We have the example of a swing set, okay, like a child on a swing set. So, equilibrium. What is equilibrium? Chemical equilibrium is a chemical reaction that can go forward and backwards. To visualize equilibrium, let's compare it to pushing a small child on a swing set. So, to start the swings, you'll pull the kid back and then release, right? Compare that to chemical equilibrium. That would be like starting um, a chemical reaction. You start with only the reactants and you mix them. Okay, then what happens? After you release the kid, they would swing down past the middle point and swing up the front end of the swing set. Okay, so that like a standard chemical reaction in a chemical equilibrium, the reactants react and create the products. Great. At the top point, the kid would stop moving forward. Okay, eventually the forward reaction would end and no more products would be made. But then what would happen? Because the kid's at the top point of the forward swing and stop, gravity will set in and the child will swing in reverse past the midpoint and swing up the rear of the swing set. So he'll go backwards, right? Okay, so this step's where an equilibrium is different from a standard chemical reaction. At some point, there will be too many products and not enough reactants. Because of this, the direction of the reaction swaps, where the products will react and create reactants. So the reaction now goes in reverse, it'll go the opposite way. Okay? Eventually, after enough back and forth, the kid will no longer be swinging, right? They'll just stop. Eventually, chemical reaction reaches a point where it's said to be at equilibrium. When a reaction's at equilibrium, the speed of the forward and reverse reactions are the same, and you've got unchanging amounts of products and reactions. So, again, the forward reaction and the reverse reaction are both still happening, but in equal amounts, okay? So, unlike the child just stopping altogether, it would be more like the reactions are still happening, but in equal amounts, forward and back. Okay. Then, to continue swinging, there would need to be some external force by either pushing or pulling the kid and allowing the swing set to work. So, once a reaction's at equilibrium, if you want to make more products or reactants, you're going to have to create a stressor and allow the reaction to proceed. The way in which the equilibrium will react with an external stressor can be determined by Le Chatelier's principle. Okay, now we're getting into Le Chatelier's principle. Here's what an equation would look like. See this double arrow? That means it can go in forward and reverse, right? And it is going in both directions. I'm not going to read everything to you, but you're going to read that on your own and take notes. So let's flip back here. Okay. So we've got here an example. Okay, so suppose you have an equilibrium established between four substances A, B, C, and D. What would happen if you change the conditions by increasing the concentration of A? Well, if we increase the concentration of A, we've got more of A. Which direction do you think the equation would go? This way or this way? You've got more of A, it would go this way, right? You've got more reactants, so you're going to make more products. So Le Chatelier's principle says that the position of equilibrium will move in such a way as to counteract the change. The position of equilibrium will move to decrease the concentration of A by reacting it with B and turning it into C and D. So the position of equilibrium moves to the right, okay, if you increase the amount of A. You go this way. Okay, what would happen if you change the conditions by decreasing the concentration of A? So you have less of A. Well, the equation would move in this direction to the left. Le Chatelier's principle says the position of equilibrium will move to counteract the change. So it will now try to increase the concentration of A. C and D will react to replace the A that has been removed. So the position of equilibrium moves to the left. Le Chatelier's principle with a change of pressure only applies when you've got reactions involving gases, okay? So what would happen if you change the conditions by increasing pressure? So let's think about this. When you're increasing the pressure, the goal would be to alleviate that pressure, right? So if you've got gas molecules moving around, if you increase pressure, that means they're going to be kind of um, bouncing off wherever, right? Faster. So there's more pressure. They're moving more quickly, right? They're hitting the sides of whatever container they're in. So pressure is caused by gas molecules hitting the sides of their container. The more molecules you have in the container, the higher the pressure will be. If you reduce the number of molecules, you're going to reduce the pressure. Okay, so that's going to help us with figuring out which direction the equation will go. If we increase the pressure, we're going to want to reduce the number of molecules. Okay, so let's see. So this is where we look at the moles, right? Because that helps us with the number of molecules, right? So there are 3 molecules on the left-hand side of the equation, but only 2 on the right. See? So 1, 2, 3, and just 1, 2. If you look at the coefficients, right? So by forming more C and D, now we're increasing the pressure, right? By forming more C and D by going to the right, you reduce the number of molecules. You go from 3 to 2, and the pressure decreases. So increasing the pressure on a gas reaction shifts the position of equilibrium towards the side with fewer molecules. Okay? Again, we increase the pressure, the equation's going to want to go in the direction where there's less molecules to decrease the pressure, right? So if we've got 1, 2, 3, and 1, 2, it's going to want to go this way to the right to reduce the pressure. What would happen if you change the conditions by decreasing the pressure? Well, the opposite would happen, right? The position of equilibrium will move towards the left because it's going to want to make more molecules because now we have less pressure. Well, now we want to increase the pressure. We want to do the opposite, right, to reach equilibrium again. What happens if there are the same number of molecules on both sides? Okay, in this case, increasing the pressure has no effect whatsoever on the position of the equilibrium. With the same numbers of molecules on both sides, the equilibrium can't move in any way that will reduce pressure. So nothing happens if there's the same number of molecules on both sides. Okay, how does changing the temperature affect dynamic equilibrium? Okay, well, it depends on if it's an exothermic or endothermic reaction, right? So for this, you need to know whether it's exothermic or endothermic, right? In this reaction, looks like it's exothermic, right? So 250 kilojoules is evolved when A and B react completely to give C and D. So you're releasing heat. Okay, 250 kilojoules is absorbed if you're going in this direction. So if the equation's going to the left, it would be considered an endothermic because you'd be adding the heat in. Okay. So what would happen if you change the conditions by increasing the temperature? Well, you can think of it as just wherever the temperature is, whichever side of the equation, if you increase it, it's going to want to go in the other side to the other side of the equation. It's going to want to reduce the temperature. So here we have an example. Okay, so if the system's in equilibrium at 300 degrees Celsius and you increase the temperature to 500 degrees, so you basically increased the temperature, right? What will happen? Okay, well, you're adding more heat. It's going to go to the left. It wants to make more of this stuff to kind of counteract that heat, right? So the back reaction absorbs heat. The position of equilibrium therefore moves to the left. The new equilibrium contains more A and B and less C and D. So think of it almost like the heat or the temperature is another reactant or product. Okay? In this case, it's a product. So if you have more of it, you're going to want to go this way to the left. But what if you decrease the temperature? What would happen if you change the conditions by decreasing the temperature? All right, well, again, Le Chatelier's principle says that the equilibrium will move in such a way to counteract the change. So the reaction will tend to heat itself up again to return to the original temperature. Okay, so here we go. The reaction will tend to heat itself up again to return to the original temperature and can do that by favoring the exothermic reaction. So the position of equilibrium will move, in this case, to the right. So we decrease the temperature here. Well, we're going to want to go to the right so that we can counteract that decrease in temperature and make more heat. Okay, so we're going to want to go to the right to make more heat. Okay. All right, so summary. Increasing the temperature of a system in dynamic equilibrium favors the endothermic reaction. System counteracts the change you've made by absorbing the extra heat. Decreasing the temperature favors the exothermic reaction. System counteracts the change you've made by producing more heat. Or if this confuses you, you can just think of it the way I explained with, well, if heat's over here and you just increased it, then it's going to go this way. If heat's over here and you decreased it, then it's going to go to the right to make more of it, right? Okay, so that's that. You're going to read all this. This gives you other examples, right? Kind of like the same idea of what we just went through. Another example problem with answers. Go through it all and then do this worksheet. You can actually type in a PDF. So what you could do is actually type your answers right in, save it, and then submit in the Dropbox. Okay? Good luck.